So up until now in this exercise, where we want to show that S is a stationary process, what we have shown up until now is we have found the distribution function of, so let me just write here, we have found the distribution function of this thing, right, of the total claim amount from time 0 to t minus s. And now we want to show that the total claim amount from time s to t actually just has the same distribution function. And since we have an expression down here, then we kind of know what we're going for. So let's just try and see if we can hit that mark. So what we want to do here is we want to look at the probability that the total claim amount is smaller than or equal to x. So let x, for you math Nazis out there, let x be greater than or equal to 0. Okay, there. And let's show that this is smaller than or equal to x. Well, let's start by writing up the definition. So this notation actually stands for the difference between the total claim amount at time t and the total claim amount at time s. And recall the definition of the total claim amount. It's this sum expression. So it's the probability that this minus this is smaller than or equal to x, right? And if we look at this, well, then n of s is definitely smaller than or equal to n of t, because n is a non-decreasing process, or almost surely non-decreasing. So the thing we have inside here is actually just a sum that starts, and so when we remove the first n of s terms, then we start the sum in n of s plus 1 and let it run up until n of t, as so. Okay, so far so good. Now we apply the same trick as we did in the earlier calculation. Now you remember that, where we condition on n. However, here we actually have two stochastic variables. We have n of t and n of s. And the thing is that n of t and n of s, they're intricately related, because if n of s is equal to 10, for example, n of t cannot be equal to 8. So n of t and n of s, they are not independent necessarily. But when we work with things, we like to put them up as independently as possible. So recall that n has independent increments. That's one of the definition points of the Poisson process. So here what we will condition on instead of n of t and n of s is we will condition on, so let me just write this up here. N of s, and we will condition on the increment from time t to s in claim number, because that we know that this increment and this increment, these two are independent of each other. And conditioning on these two things is actually equivalent to conditioning on n of s and n of t, because they contain the same information. If you know n of s and you know its increments up until time t, then you also know n of t and vice versa, right? So we're conditioning on the same amount of information, so we're safe here. And then, again, we will want to calculate the mean value of the thing that's inside here for different outcomes of n of s and n of s to t. And now we have to be a bit careful, because n of s and n of s to t, well, each can attain different values, right? So what we have inside here is we have this thing for xi equal to x given n of s is equal to, well, let's just say m, and n of s to t equal to, let's say, k. And the reason we do this is, well, we want to find the expected value given different outcomes of n of s and the increment n of s to t, and, well, they can both attain different values, right? And this is Poisson distributed, and this is Poisson distributed, so both m and k can take values from 0 to infinity. Now, I know that this might seem a bit complicated to you guys, but just think about it. Like, actually what we're doing is we're just finding the mean value of something, and that's it. So these are the different outcomes we have, these are the different combinations, and we multiply each outcome by the probability that it will occur. So multiply by the probability that n of s is equal to m, and that n of s to t is equal to k. But the thing here now is, recall that n of s and the increment from s to t, n of s to t, they are independent increments in the Poisson process. Oh, that's nice. And that's nice because now we can split this probability up into the product of two probabilities. And that was the reason why we looked at the increment here instead of looking at n of t. Okay. So let us just try and continue, because all of this here, this is inside the double sum. And that's not really that pretty, because we want to end up with something that looks like this in the corner. So what do we do now? Well, first of all, let's try and see if we can do something about the boundaries in this sum. Well, maybe we can. How do we do that? Again, let us just recall here that this, what on earth am I doing? Let us just recall that this thing that we have, the probability of blah blah given blah blah, is just the probability of A given B. It's a probability of one event given another event. So we can write this up as, if we just call this thing here, if we call this thing here, we call it star, I can write that star is equal to the probability of the sum from n of s plus 1 to n of t, xi is more than equal to x, and intersected with the event that n of s is equal to n, n of s to t is equal to k, and then divide by the probability that n of s is equal to m, the probability that n of s to t is equal to k. So same concept as earlier. The fun thing now is just that we have two variables, but that won't stop us from achieving our goal, because let's just look at this. What can we do? Well, the event here intersected with this event here is the same as the event that we plug these values into the summation. So it's the same as the event that we start in m plus 1 and run all the way up to n of t, which is actually n of s plus the increment from s to t, so that will be m plus k. I think I did an error here in the exercise class, which I must apologize for, but yeah. So this event here is the same as this event intersected with this event. However, now we have that this event is actually independent from this event, so I can take this out into a separate probability. And these two are independent, so I can also just take these two out and divide by the denominator. And I guess you guys can already see where this is headed actually, so probably I don't even need to finish off this calculation, because now this cancels with this, and the only thing I've got left is just this probability that the sum of xi from m plus 1 to m plus k is smaller than or equal to x. Now let us use one more of our assumptions now. So which assumptions have we used? We have used the x is independent from n, and we have used, we have not used stationarity of n yet. But let us now use that the xi are IID, because the nice thing about that, xi are IID, the nice thing about that is that then the distribution of xm plus 1 up to xm plus k is the same distribution as x1 up to xk, right? So that's the nice thing about IID variables. It's kind of like they're independent and they have the same distribution, so I can just x1 and x2 have the same distribution as x2 and x3, and so on and so on. So this is just equal to the probability that the m first, that the k first xi's are smaller than or equal to x. And of course the reason why I want to do this is because, that's where I want to end up from the result from earlier. Okay, so what have we achieved now? What we have achieved is we have achieved showing that the star, so this first part of our expression up there, is equal to just merely this thing. So we've taken a rather complex expression and turned it rather simple. So now let us continue our original calculation, which is now equal to, so we still have the double sums, and now the entire first row we have established is equal to the probability that the sum of the first k xi's are smaller than or equal to x. And then we multiply by the probability that n of s is equal to n, and the probability that n of s comma t is equal to k. Okay, so now let us continue a little bit. We want to end up here with this. So one thing that we can ask ourselves is, well, there is definitely no m in the expression here, so we need to remove the m. So let's look at this. Well, the nice thing now is that the only thing that depends on m inside our sum is this term, because the m has vanished from this term since the xi were IID. So what can we do now? Now we can take this term outside of the summation. As such. So what we have now is just a sum of the point probabilities in a Poisson distribution for all the outcomes that you can have. And this sum is equal to 1. So this cancels out. And what we have left is, well, what do we have left? We have, what we have left is this. So the sum from 0 to infinity of the probability that the first k claims together are below x, and we have this here. And we're almost finished, because recall that we want to end up with this, right? We want to end up with n of t minus s. What we have now is the increment from time s to t. And the way we turn that into n of t minus s is by recalling what? Yes, by recalling that N is a homogeneous Poisson process, hence it is stationary. And that means that as long as the interval length, the time interval length is the same, then the increment on that time interval in claim number will have the same distribution, no matter where we look on the time axis. And now we are done, because now we have shown that both the claim size, total claim size amount from time 0 to t minus s is given by this expression, that its distribution function is given by this expression, and that the distribution function of the total claim amount from time s to t is given by the same expression. So that was a very, very long proof. Thank you if you followed through it all the way. It's just a really, really good proof to understand the basic concepts of certain conditioning elements and how we use the assumptions. So look through it again if it was confusing, and see you guys in the next video where we do this much faster by using characteristic functions.